All right, let's start talking about searching algorithms. And in particular, we'll focus on two algorithms, linear searching and binary searching. So let's start off with some questions. First, what is the idea of a linear search? Well, it's probably the most naive way you can come up with for how to search for an element in a list. You start at index 0, the front of the list, and from left to right, you check every element in the list and compare it to see whether it's equal to the key you're looking for. Once you find it, you're done. Otherwise, you go through every element till you get to the end and you report not found. So we can do that. It's pretty straightforward to think about, but it's also very slow because we have to look at every single element. Whereas we might be able to exploit some property of our list to do a much faster kind of search. Now, a much more efficient way of writing a search algorithm is doing a binary search. And a binary search does not have to search through every element in the list. Instead, it starts at the center of the list and compares that element to the key that we're looking for. And based on that, it will decide whether to go left or right. So every time we make a comparison, we are cutting off half of the array, which is a much more efficient search. And we'll talk about this more in detail later. So why not always do that? It sounds much better than a linear search. Well, it requires that the array is already sorted in order to work. If your elements aren't in any order, then going left or right only doesn't make any sense. The list has to be applied, or the list has to be sorted first. Whereas a linear search can be applied to any arbitrary array without any sorting, and even if the elements cannot be sorted at all, you can still run a linear search. Now let's trace through some code for what a linear search might do. So here's some code. It has a loop that runs from I equals 0 to the length of the array, and for every element, it checks whether that element is equal to our key that we pass in. If it is, we return that index. Otherwise, we return -1. So let's say we have this array containing the letters B, C, F, E, and A, and we want to search through that list. So every time we execute this line, line 3, we are doing a comparison. A comparison is whenever we check whether our key is equal to some element in the list. So how many comparisons are needed if we're doing a linear search for the key A? Think about it. The answer is 5. We have to do a comparison for each of the elements that aren't A, B, C, F, and E, and then one final comparison to see that the fifth element is A. So we return I equals 4. What about if we're doing a linear search for the key M? Think about this. And the answer is, again, 5. So M is not in the list, but we don't know that until we've checked every element in the list against M. And that requires the same number of comparisons as before, or 5. So in general, if we're running a linear search for a key in an array of size n, how many comparisons are needed as a function of n? Well, in the worst case, it could take n elements. We have to check every single element in the array, and if the array is of length n, then we have to do n comparisons. So linear search works in the general case, but it's pretty inefficient. Now we'll look at our more efficient searching algorithm, a binary search. So for this example, we're going to be searching in a list of numbers that contains every number from 0 through 128 in ascending order. And we're looking for the number 77. So the general idea behind a binary search is we want to not look at every element, and instead we're going to split the array after we make each comparison to either look at the left half or the right half of the array. And so instead of shrinking the size of the array we're looking at by 1, each time we check an element, we're going to be shrinking it by half each time we check an element. So to do that, instead of just keeping track of the current index we're looking at, as was the case for linear searching, we're instead going to be keeping track of two indices, a low and a high. And the low and the high are going to represent the region of the array that we're currently searching through. So to start out, this is going to be the entire length of the array. Then the first thing we'll do is we'll check our base case, which is if high is greater than, or sorry, if high is less than or equal to low. If that is the case, we say the algorithm is finished. We did not find our element that we're looking for, and we'll return -1. So if high is less than or equal to low, we return this. Otherwise, high is greater than low, and we'll go on with the rest of the algorithm. So to decide which element to look at next, we're going to compute the middle element in between our boundary region defined by low and high. So to do that, we're going to compute low plus high minus low over 2. That's going to give us 64, the middle element. Then we'll compare that element at position 64 to our key. And if that element's greater, we're going to only search in the left half of the array. Because let's say our key was, I don't know, 30, for example, and if 64 were greater than 30, we would trigger this case. And we'd say, okay, well now we only want to look in the left half of the array. But in our case, we're searching for 77. So instead, we're going to go to this case. If our middle element is less than our key, and 64 is less than 77, so we're going to hit this case. And in this case, we're going to make a recursive call to binary search with our same key and array, but we're going to update the value of low to be mid plus 1. And what that says is now our low is going to be only the right half of the array. So we'll stop looking at anything to the left because we know 77 is greater than 64, and because this is in sorted order, our element has to be on the right side. So we're going to only look at elements to the right of 64, and we do that just by updating our index of low. High stays the same because it's still the right end of the list. Otherwise, if we found the element we're looking for, then we'll return mid if our array at element mid is equal to our key. And that says, we're done, here's where we found our element. And so we continue this process. We'll then be looking in the region of 64 through 128. And we will again compute the middle element, which in this case is 96. And we'll say, is 77 greater than 96? No, it's not. It's smaller. So then we'll hit this case. And in this case, we make a recursive call with our same index of low, but now we set high equal to mid. So we're now cutting off the right half of the array to the right of mid and saying now we're only going to focus on the elements from 64 through 96. And we'll continue this process all the way until we have found our single element 77, and we return that. Now, one question is, why do we use this fancy little low plus high minus low divided by 2 to compute our mid, instead of just doing low plus high divided by 2, which is a much simpler way of computing the same thing, right? Well, this question actually stumped computer scientists for many years. The low plus high divided by 2 computation was implemented in Java for many, many years, until some computer scientists discovered that it actually contained a bug. And that bug is that if low and high happen to be very large numbers, then computing the value of low plus high might actually overflow the maximum value of an integer in Java, which would cause this algorithm to fail. So to accommodate for this, a subtraction was used instead, and we then compute low plus high minus low divided by 2 to get the midpoint value without causing any overflow. All right, now we're going to have you try tracing through some binary searches on your own. So here's an array containing 5 elements, B, C, F, G, and Z. And let's say you want to run a binary search for the key Z. So fill out this table below. You might need some extra rows to figure out how many function calls are made, so how many comparisons are being done, as well as what are the values of low, high, and mid at each function call. So take a bit to fill out the table. Okay, let's start talking about this search. So to start off, our low and high will be set to 0, the start of the array, and 5, the length of the array. And we'll compute a midpoint of 2, and 2 corresponds to the letter F. So we'll compare whether F is greater than, less than, or equal to Z. F is less than Z, so we're going to hit this case, and we'll chop off the left half of the array by setting our low equal to mid plus 1. So at the next function call, our low will be 3, our high will be 5. So at this point, our mid is 4, and the element at position 4, index from 0, is Z. So we have found our element Z, and we return mid. So the total number of comparisons that were made was 4, because each of these lines corresponds to a single comparison. So we compared, is F greater than Z? False. F less than Z? That's true. And then in our next call, we compared, is Z greater than Z? False. Is Z less than Z? Also false. And then we returned it. So in total, we made 4 comparisons, and we inspected elements at index 2 and at index 4. Now let's try another tracing of a binary search, but this time the key we're looking for, A, is not in our array. So just like before, fill out the table of function calls and give the values of low, high, and mid, and the comparisons that are done at each step. Okay, now let's start working through this one. So to start off, just like before, our low is 0, our high is 5, and then we compute a midpoint of 2. So that's our element F. We check if F is greater than A. It is, so we will chop off our high and set high equal to mid, and make another function call. In the second function call, high is now equal to 2. So then our mid element is 1, and we check whether C is greater than A. It is, so we again set high equal to mid, and make another function call. Now our low is 0, and our high is 1. Our mid element is 0, so we compare B to A, and B is again greater than A. So once again, we set high equal to mid, 0. And at this point, low and high are equal. That hits our base case, so we return -1 because A was not found in the array. So in total, this run took 3 comparisons, and we compared to the indices 2, 1, and 0. Now that you've done some tracing of binary searches, it's time to write one of your own. So for this problem, we want you to write a non-recursive version of binary search. So the version we presented before was recursive. This time, try writing an iterative version of binary search. And then trace through your code, searching for the keys A and Z with the following array. And just like previously, show the values of low, mid, and high at each step, as well as how many comparisons are done at each iteration of the loop. Then we'll present one of our solutions and trace through it for these examples. So give yourself some time to write a non-recursive version and trace through. All right, Now that you've had a chance to write an iterative version of binary search, let's see how it compares to ours. So here's one way you might write an iterative version of binary search. We're going to change the base case from our recursion into the while condition for our loop. So we'll use the condition when as long as low is less than or equal to high. As soon as we violate this condition, then our loop will terminate and we'll exit the function, returning -1. So our base case becomes the while condition for our loop. And the rest of the code will progress similarly. We'll compute the midpoint. And then here, we'll first check whether the element at mid is equal to our key. And if it is, we'll return that element, or that index. Otherwise, we'll check whether A at element mid is less than our key. If it is, we'll set our low equal to mid plus 1, chopping off the left half of the array. Otherwise, we'll set high equal to mid minus 1, chopping off the right half of the array. Now, there's two main differences you should notice about this approach. One is that we are now setting high equal to mid minus 1 instead of mid. The reason for doing that is just to show you that there's different ways of writing binary search with slightly different settings of high or low, along with a slightly different base case, or in this case, a terminating condition for our while loop. So for this example, we will terminate whenever low is greater than high. And to accommodate for that, we have to set high equal to mid minus 1 instead of mid. The other thing I'll point out is that in this example, the array at our comparison to see whether our middle element is equal to our key now occurs before we check less than and greater than instead of after. Why do we do that? Well, simply to make the tracing of the algorithm more interesting. So let's roll with it. So here's what it might look like if we trace through this algorithm, searching for the key A, which is in the list. So we'll first start off by setting low to 0, high to 4 instead of 5. Now this is important for making our new setting of high equal to mid minus 1 work. And then our mid will be 2. The second element is D, or index from 0 is D. So we'll first check whether D is equal to A. That is false. Then we'll check whether D is less than A. That's also false. So finally, we'll set high equal to mid minus 1. And run the loop again. So is loop less than or equal to high? Yes, it is. Low is 0 and high is 1. So then we'll get our middle element, that is index 0. And then we'll check that element A against our key A. And we have found our key, so we're done. And the total comparisons that were made were 3. Now let's try an element that does not appear in our list, Z. So to check for Z, we'll start off just as before with low 0, high 4. Our middle index will be 2. That's element D. So we'll compare whether D is equal to Z. That is false. Then we'll check whether D is less than Z. That's true. So we'll set we'll set low equal to mid plus 1, which is 3. Then we'll compare our middle element, which is now 3, with Z. That's G. G is not equal to Z, but G is less than Z. So again, we'll set low equal to mid plus 1. So low and high are now equal, but our base case says if low is equal to high, we keep going. So now we get a mid of 4, and that's our element M. So we check, is M equal to Z? Nope. Is M less than Z? No. Yes, it is. So we'll then set low equal to mid plus 1 again. So now our low is 5, and high is 4. that hits our terminating condition because 5 is greater than 4. So our loop terminates and we return -1. So the total number of comparisons now were 6. Now let's look at one final problem about binary search. This time, your goal is to modify the binary search algorithm we've given in order to find the least index of duplicate keys. So previously, binary search would simply return the index of the first place in the array where it found the key you passed in. But this time, we want to find not just any such position of the key, but the least position. So, for example, in an array with 3 A's, if we're looking for the key A, we want to return 0 and not 2. So think about how you might modify binary search to accommodate this problem. All right, let's start talking about this problem. So in order to accommodate finding the least index of our key in the case of duplicates, we need to focus on what happens when we find some element in our array that's equal to our key. Previously, we could just return and say, oh, we found it, here's the index. But now, we don't just want to return that element because we don't know whether or not that element is in fact the minimum element of that key, or if there's duplicates. And if there are duplicates, the minimum element of the key has to be at most the mid, but it could be less. So that tells us when we find an element in the array that's equal to our key, we don't want to end the binary search yet, but instead we want to start looking only in the left half of the array until we've determined that yes, this element is actually the minimum index. So to do that, we're going to modify our comparison to check whether the middle element is greater than or equal to our key. So before, if our middle element were greater than the key, we knew we wanted to look in the left half of the array. So we would change our high to mid, cutting off the right half. But now we also want to do that when we find an element that's equal to the key. Because now we just want to look in the left half to see whether or not that element is actually the minimum element, or if it's not, to find the minimum index of the key. So we'll change this comparison to be greater than or equal to. And the other change we have to make is in our terminating conditions, our base cases. So now we'll say that when high is equal to low, we'll return low. And this says that when our boundary has converged on just a single element, then we can assume that that element is in fact our key, and it is the minimum such index of that key. Otherwise, if high is less than low, so high has crossed low, then in that case we'll say that our element was not found in the list, and we'll return -1. All right, so now let's trace through this algorithm by searching for the key A. In particular, we want to find its least such index. So here's what that looks like. We start off by setting low equal to 0 and high equal to 4. This is important for getting our case where high is equal to low to work. So first, mid will be index 2. So we compare this A to A, and we see they're equal. So our algorithm continues by setting high equal to mid. So now low is 0 and high is 2. Our mid index is 1, so we compare this A with A. That's true again, so we do another call, where low is 0 and high is now equal to 1. Our mid element will be 0, so we compare this A with A. We see that's true, so we again set high equal to mid. Now both low and high are 0, so that's going to trigger our base case, high is equal to low. And in this case, we return 0, low, that is our index, the least index of A. So in total, we'll say this took 3 array comparisons with this A, and this A. Let's wrap up our section on linear and binary searching with some questions. First, what is the best and worst case performance of running a linear search? Think about it. The best case performance is when the search key is among the first k elements of your list, where k is some constant. The easiest way to think of this is, let's say the element you're searching for just happens to be at the very first position. So k is 1 in that case. When that occurs, your algorithm is considered to be constant time, because you didn't have to look through the whole array. You found it at the first element and you stopped. But the worst case is when your key is not in the array, because then you have to check every single element in the array to know that for certain. And that takes linear time, or big O of n. Next, what are the best and worst case runtimes of a binary search? Well, a binary search is considered a divide and conquer algorithm because it chops off half of the list at each step after making a single comparison and reduces the search space by 50% each time. So this leads to an algorithm with a logarithmic worst case performance of log base 2 of n. Base 2 because we cut in half each time. That's the worst case performance. The best case performance, however, is still constant time, because if your element you're searching for just happens to be the middle element of the array, then you're going to find it immediately when you start the search. So again, the best case is in fact constant time, but the worst case is logarithmic time, much better than a linear search. But just keep in mind that the array has to be sorted first to use binary search. Finally, what do we mean by logarithmic performance? Well, let's talk about this in more detail. So let's say your array has n elements in it. It's of size n. Now, assume that n is equal to some power of 2. So it's 2 to the k for some k, which generally when we do analysis for some large n, we assume this. So if we assume that n is equal to 2 to the k, then we take the log of both sides, and we get log 2 of n is equal to log 2 of 2 to the k. And that becomes equal to, using our log rules, log to the n is equal to k. So in each iteration, the size of the array shrinks in half by dividing the array of size 2 to the k times, until we get to 1. A single element. So that means our performance is roughly on the order of k. And here we find that k is equal to log base 2 of n. So overall, the performance is big O of log base 2 of n, or logarithmic.